Hello, everyone. I welcome you back to our WestPack Hub, our education center here at WestPack. 3 full days of education, so please drop in and out as your schedule permits. I'm very excited today to bring to you our next presentation, Mission Possible, formulating the right adhesive coating for the application. Our speakers today are Kevin Zacharias and Rick Brady of Oliver Healthcare Packaging. Kevin is the Global Technical Director at Oliver Healthcare Packaging and is responsible for product development and technical service. Prior to joining Oliver, Kevin was a manager of packaging development at Baxter Healthcare and a packaging engineer at Roche Diagnostics. Rick is the technology manager at Oliver Healthcare Packaging. In this role, Rick is responsible for research and development, coating formulation, technical support, and validation for new coating technology. Prior to joining Oliver, Rick spent 20 years as a research scientist at Hercules Incorporated, where he worked on polymers for electronics, paper, chemicals, and wood adhesives. Now I welcome Kevin and Rick.
Thanks, Daphne. So I'm going to start us off talking about adhesives. And just to be clear, when we're talking about adhesives, we're talking about the adhesives that are involved with sterile medical device packaging. Commonly, you'll see them coated onto DuPont medical grade Tyvek, medical grade papers, films, and foils. So that's what we're talking about. They're a very important part of the sterile barrier system. They're part of the system that allows for sealability and then peelability to give you that aseptic presentation. It also decreases the risk of fiber tear when you're working with different types of materials. And they all need heat to make them work. So for medical device manufacturers, the heating process, that'd be the sealing process. So where you've got heat, pressure, and dwell time to make that adhesive work, activate, and create a peelable seal. So we're adhesive manufacturers and formulators. So we're going to spend a big part of this presentation talking about the formulation aspects of our adhesive coatings and how to formulate for different applications. So I'm going to focus to start off with peel strength. So you think about the usability in the OR with the clinical setting, clinicians. They're really opening the package, creating aseptic presentation into the sterile field. So if you formulate the adhesive coating to be too strong, things like that can happen. You can get substrates to tear. That's a bad thing because you can't aseptically present the medical device into the sterile field. We can also tailor the adhesive seal strength for user experience. So think about clinicians again, grabbing peel tabs, opening pouches, opening lids on thermoform trays. That usability, that user experience is part of the application as well. We also formulate our adhesives to create a seal verification. So that nurse, that clinician in the hospital setting can peel back and they can see the outline on that package on the film. They can see there's a complete seal, an integral seal, no breach of sterile barrier. On the flip side, if we're formulating and the seal strength is too weak, you can have risk of open seals. That's obviously a bad thing. If you think about some of the sterilization modes of the medical device, you have EO sterilization. There's a lot of elevated temperature, pressure. Seals that are too weak can open up, and that's a problem. And also risk of open seals during distribution and handling. So it's really important when you look at the adhesives that we're talking about today to understand how they work. They're formulated to work cohesively. So in this diagram you can see on the top we've got medical grade Tyvek, for example. You've got that adhesive layer, and then you've got the film. It could be a tray flange that we're looking at. So if you look at that lower left diagram, you can see when you peel that lid up, when the clinician is peeling the lid off of the tray, that adhesive is designed to work cohesively. So you get a split in the adhesive right here. So when you lift the lid off of the tray, some of it's going to stay on the tray, and some of it's going to stay on the Tyvek. So just understand the basics of how the adhesives are formulated to work. So this is just a quick video showing you a magnified view That's like a side view of a lid being pulled off of a tray flange, and you can see the adhesive cohesively splitting and staying on the film, and some of it staying on the lid. So I'm going to turn it over to Rick Brady to talk about some of the formulation aspects of the coatings.
Types of adhesives, the hot melt adhesives and the water-based adhesives, and there's a lot of commonality in the formulations, really. We start with the base polymers, which are typically ethylene vinyl acetate copolymers. We do use other polymers for specialty applications, but the basic hot melts are EVA polymers. We use waxes, and that's largely to control this peel strength, adjust the cohesive strength of the adhesive. Waxes also serve to help with anti-blocking. That's so you can coat and roll the coating up on itself without it sticking to itself. And then we have resins. These are what people call hydrocarbon resins or tackifier resins, and these are to give specific adhesion to both the substrate, or to the coating substrate and the substrate that you're sealing to. And the optimum resin system is going to be different for different substrate systems. In some cases we use fillers. They're somewhat similar to waxes, can control the cohesive strength. And then the only real difference is in the water-based system. Think of it like a latex-based paint. That's how it's delivered onto the Tyvek or paper or other substrate. You have the water and the surfactant, and then the water is dried off. But that's really the only major difference in the formulations. So here, this is a kind of an overwhelming chart, but basically if you look down the left side, there are different properties, and the formulation ingredients are on the top. So it basically shows if you're, for example, we're concentrating right now on the cohesive strength, because that's what's getting our peel strength. So for cohesive strength, if you increase the wax, it'll decrease cohesive strength. If you increase the resin, it'll decrease the cohesive strength. If you increase the polymer, it'll increase the cohesive strength. So the arrows are giving you the direction that each component will get you generically. Filler will decrease the cohesive strength. And you can see, I won't go through all these, but we have a good idea of what properties, how to get the different properties with the different ingredients. Okay, so again, as we were talking about, you need to control the cohesive strength to tailor the seal strength. And again, so from that chart, then directly, if you want to get low seal strength, you need high wax, high resin, low polymer, high filler, and the opposite is true for high seal strength. Okay, I'll pass it back to Kevin.
So we're going to talk about some real-world case studies. Obviously not going to share names, but these are scenarios that happened along the way with some of our customers. This first one was a situation where we needed to increase the seal strength. This customer had been using some of our adhesives for quite some time, had success, but they had a very heavyweight medical device, much heavier than any other device that they had been packaging. And it was a form fill seal machine. So horizontal thermoform fill seal machine was part of the situation. So we were supplying roll stock in that scenario that was coated. So they were having problems with seal failures. You can see some of the little scalloped or void areas in the seal around the perimeter of that package. So those are the types of things that they were seeing that were causing problems. So we went back to the drawing board, or back to the formulation board, and if you think about some of the things Rick just talked about, we tweaked ratios in the standard formula to increase seal strength to get us over the hurdle. This is a chart that shows seal strength output. So basically you can see the original formula is the blue line. That y-axis is the seal strength in pounds per inch. So the legacy product was tracking around 1.5 pounds, a little bit higher than that. The reformulation, we were tracking closer to 2 pounds. So we were able to get a higher output by just changing the ratios of the components, and that was a big win for the medical device manufacturer. We also did some things to improve hot tack strength. So if you think about a form fill seal application, you've got intermittent motion, you've got a heated platen coming down, and that machine is moving, so you've got all that activity going on. We did some things with that heavyweight device pulling down on the web. Think about the hot tack strength that's required in that adhesive to prevent failure. So we did both those things with the change of ratios. So this is another real world case. I'm going to let Rick talk about this one.
Thanks, Kevin. So this is the opposite of what Kevin just talked about. He talked about increasing seal strength. In this case, we had a customer that wanted weaker seal strength. They felt that peeling off of the trays was too difficult. We had an alternative product which we called TPT 0234. We kind of refer to it as a soft peel, but they felt that was too weak. So we went back to the formulation board, and we basically formulated adhesive to give intermediate peel. We basically dialed it right in. So here you can see the result. Then this on the left side is the peak bond strength in pounds per inch, and we have the temperature, the seal temperature, on the x-axis, and the top line there is the sort of the standard product, the TPT 0260, the green line. The bottom line was the so-called soft peel, the 0234, that's the purple, and we formulated to go right in the middle. And they were happy with it, and it met all their requirements, and they went forward with it. Okay, pass it back.
So one last case study. This one was related to ethylene oxide ETO gas creep, so seal creep during EO sterilization. And it was a reinforced coated paper, and it was a horizontal form fill seal application. In this particular situation, the manufacturer of the device had shifted EO cycles to a much more aggressive cycle, and they got through validation okay, but over time they started seeing very low occurrence rates of open packages. And that picture on the right side, you can kind of see that's a dye penetrant test failure. You can see the blue dye is leaked through the side seal. So there was a very low occurrence rate. It was hard to track exactly what the root cause was, but it was basically determined to be a combination of the porosity of that top web. So think about breathability. If you have reduced breathability, what does that do? That puts pressure on that lid, creates pillowing, creates stress on the seal, and also the creep resistance of the adhesive that was being used. So creep resistance meaning, think about EO, it's warm temperatures, it's humid conditions, it's pressure, inflow and outflow of gas, so you want your adhesive to be strong at those elevated temperatures. So just a quick pictorial of what I'm talking about. Again, you've got elevated temperature, stress on the seal from the vacuum, lid porosity, and that again is a nice picture of seal creep produced during EO sterilization, those little scalloped areas. That's where the adhesive is starting to give way and you're getting partial open seals, and in some cases, in this particular situation, the seal opened all the way. A nice pictorial. This is actually something we use when we're talking to customers, and this particular customer said, hey, that looks just like the geometry of our package. So what you want to have is on the left picture, think about trying to help you visualize. If you've got more breathability in your top web, less pillowing, less stress on that seal. The picture on the right, you got more pillowing, more stress. If that adhesive is not strong at the elevated temperatures of the EO cycle, you get a blown seal. So Rick's going to talk through what we did in this particular situation to help with the sterilizer creep.
Okay, if you remember that chart that I showed in the different ingredients and the different properties, seal creep wasn't on there. There's a few extra complications, so I kind of broke this out separately. So first of all, you wanted to get higher porosity, and just to be clear, there's a test called Gurley test where the lower you get in that test, the shorter time to force the gas through, it means higher porosity. So that's what you want to get. So for water-based coating, some things that are important are the choice of the polymers. Obviously for porosity, you don't want to have a film former, so you need to maintain some pores in the coating, so that drives your choice of polymers. Also the levels of wax and resin, generally when you get higher levels of wax and resin, that gives you a more open structure, and that can increase your porosity as you desire. And then a third thing is optimizing particle size. So this is really a processing thing when we're producing the adhesive. By adjusting the parameters, we can control the particle size. We measure the particle size, and if you, for example, if you get those particles too small, they start to close up those small pores. So that's an important consideration. On the hot melt side, it's a little different because as you can see in the picture on the bottom right, we're basically printing islands of hot melt, and there's open areas there. In between the sort of the pyramids, that's raw Tyvek. So the gas in that case can get through, the EO gas, and in that case, so that's a natural advantage of hot melt, is that there are fully open areas of Tyvek, and so you naturally have this good porosity that you need for sterilizer creep. So the other part of sterilizer creep is maintaining this high strength at elevated temperature and humidity, so mimicking EO conditions, which typically might be a 55 C and 90 or 95% relative humidity. So again, you have your choice of polymers. Obviously, if it's going to see 55 C, you want the melting point to be significantly above that. And also molecular weight's always important in polymers. As you approach the melting point, there can be something sort of like pre-melting, but if you have high molecular weight, that kind of resists deformation, and that's helpful. So in this case, high molecular weight is a key component. And then you need the proper resin package for robust adhesion. And so that's what we talked about earlier, the tackifier resins. In this case, they need to keep that adhesive stuck under high humidity conditions. So it's really a robustness of adhesion. And sometimes you can have good room temperature adhesion, but under high humidity, the moisture can get to the interface and tend to debond. So you need the really good resin, the right resin for the right substrate. And then, of course, you always have the ingredient ratios for the optimization. So here's a test that we do. This is actually, I'll run this a few times so you can see it. But basically what we do, this is inside a humidity chamber, temperature and humidity, so we can run it at the 55 C, 95% relative humidity. We hang weights on it, so this would be stress, mimicking stress under those conditions. And so let me just go back and start it again. Here we go. And you can see it's sort of legacy material. This is time lapse, was dropping off fairly quickly, and we had an improved version optimized for seal creep was on the right side, and you can see it was quite a bit difference in its performance. So kind of see that in graph wise, here we have on the left side the time until failure, so that would be the time for those weights to drop off, and we have at three different seal conditions: 230, 250, 270. You see the legacy adhesive was dropping off in the order of 10 minutes, and this reformulation version is basically doubled that, so a significant improvement. And also with that formulation, we were able to get that improved creep resistance or improved strength as well. We were able to improve the porosity. And again here, this is higher porosity at a lower Gurley. This is a Gurley seconds on the left. And legacy material was around 75, and we're coming with the reformulation around 50 seconds. So that's an improvement in that way as well. So we had improvements in both areas. Okay, I'll pass it back to Kevin then.
So we're going to switch now and just show some of the coating processes. It's always helpful to understand. We've talked about some different applications. We've talked about the formulation aspects. And now we're just going to run through a few slides to show the actual coating process to help visualize how we're laying this adhesive down onto the substrates we're talking about. So Rick talked about earlier on kind of two different formulation or two different adhesive technologies, the hot melt and the air knife coated. I'm going to just talk about hot melt real quick. So that's the picture in the upper right corner. Those blue dots are basically what Rick was talking about. We're printing or laying down dots of hot melt adhesive onto, in this case, the picture is medical grade Tyvek. You can see the fibers of the Tyvek in between the blue dots. So basically it's just depicting here almost like a gravure type cylinder, laying down those micro dots. There's a doctor blade that is scraping off the excess adhesive off of the cylinder before we're laying down those dots onto the substrate. So that's an animation. We'll show you a quick rundown of the actual coating process. You can see master rolls. We're printing the adhesive or coating the adhesive roughly 55 inches wide. Goes through a series of rollers. And then you'll see a silver colored cylinder here. That's that etched cylinder that I was just talking about. So it's picking up micro dots of adhesive. It's got etched micro pockets picking up the adhesive out of the fountain. The doctor blade is scraping off the excess adhesive. And then that impression roll, basically in between the interface of that impression roll and that silver cylinder, is where we're laying down that adhesive coating. Then it's going to go through a series of chill rolls. It's all done, the adhesive formulation manufacturing is done at elevated temperature, so it's a heated process. So we're laying down molten dots of adhesive onto the Tyvek in this case and getting them to set up and chill quickly. So Rick's going to talk about the other coating technology that we have at our disposal.
Okay, the other process is for water-based adhesive, and again, think the adhesive is carried by water. It's somewhat similar to a latex paint, but basically you have material coming into the applicator roller, which is picking up adhesive, laying it down on the bottom of the substrate, and then you have what's called the blow-off pan. And basically, an air knife is a non-contact method. So instead of think of it as using air as a doctor blade. Basically, you're blowing off excess adhesive into the blow-off pan. So that's what's basically controlling your coating weight. By controlling the air pressure in the air knife, you control your coating weight. And here's another version where you can see the overall process, which is the uncoated roll going through the air knife, and then in this case, of course, different than hot melt, you need to dry off the water. So you need a fairly long oven, you dry off the water, and then you get to the dry end. And here's the picture. On the left side, or now toward the middle, you can see the web going up into the oven. So that's after the air knife goes through this long oven. You can see how much oven is needed in order to dry it off. But now we're coming back down, and you can see the air knife is in this. It's a little hard to see if we can see it. The air knife is right in this area here, blowing off material, and then the web's going up. So that's the basic process for air knife coating. Okay, and all right, we'll be happy to answer some questions.
Okay, thank you.
All right, if you do think of some questions, you can welcome to come to our booth. It's 2038.
2038 is our booth. Thank you.
Thank you.